Welcome back to Nemeth. Today, let's tackle upper elementary math. We're looking at things commonly taught in grades 3, 4, and 5. Remember in Nemeth that it's important to be able to code switch in and out of Nemeth. So generally, math worksheets, math books start off in a UEB context because a lot of writing is just writing. Instructions and things need to be written in the regular literary equivalent Braille code, Unified English Braille. So you'll switch into Nemeth using your Nemeth switch indicators and switch out when you're done. But in the context of a math class, by this age, students might have a lot of problems that are all the same type. If there are no words intervening, or maybe only one word here or there, it's really worthwhile to switch into Nemeth, put lots of problems of the same type together all in the Nemeth code, and switch back out. So remember that if you're doing that and you've got things like a list A, B, C, that it's important to use that punctuation indicator, the .456, before any regular sentence punctuation, like the periods after the letters. Also in Nemeth, we use an English letter identifier in front of the A, B, C, D, even for the letter A, even though there's no alphabetic word sign that could be that. It's really nice. It makes the spacing all line up, and it's easier to find where the problems start. By upper elementary school, students start to learn fractions. Fractions are one of those parts of math that you actually keep using forever because it's so functional. Fractions in Nemeth always use an open and close indicator. The open indicator for fraction in the Nemeth code is dots 1, 4, 5, 6, and close is 3, 4, 5, 6. But don't worry, you'll never confuse it for a numeric indicator because it happens at the end of something instead of at the start in this context. Opening a fraction always sets numeric mode, so things will have their numeric mode meaning within the fraction. You won't have to use a separate numeric indicator to identify numbers. I have a couple examples here. The example 1/2, so open fraction indicator. Remember, anything that's called an indicator in Braille, you don't write anything for that cell when you write the print equivalent. It just tells you what the other cells coming next mean. So open fraction indicator, the number 1, which is Braille dot 2, the fraction line, dots 3, 4, the number 2, dots 2, 3, and then the close fraction indicator, dots 3, 4, 5, 6, let us know that we're done with the fraction. So that's the fraction 1/2. I have another example here, which says 89 over 100, written as a fraction. Again, you see there's that open indicator at the beginning, the numerator, the fraction line, the denominator of 100, and the fraction close indicator. Fractions can be more complicated than just a number on top and a number on the bottom, and when that happens, it kind of builds on that sequence, building out from there. A mixed number does start with a numeric indicator for the whole number only. So you'd have a numeric indicator. My first example is 3.5. So I have numeric indicator 3 to set up the whole number. And then I have a different kind of fraction opener for the mixed number that tells me this fraction is connected to the preceding number. So I have the 4, 5, 6 prefix and then my fraction opener. So it's not a standalone fraction, it's a fraction within a mixed number when I see that indicator. And then I have my 1/2 written. And when I close the fraction within a mixed number, that close needs to match the open. So if I opened with a 4, 5, 6, 1, 4, 5, 6, then I close with a 4, 5, 6, 3, 4, 5, 6. So it's got that same matching prefix both places. Just like if you opened a curly brace, you'd close a curly brace, or if you opened a square bracket, you'd close a square bracket. We always make our prefixes match. You can have fractions that are not written vertically, one over the other, that you might write with a forward slash. That's okay. If you need to write it with a forward slash, you still put the fraction indicators around it so I can tell that it's a numerator and a denominator, even if it's kind of on the angle instead of straight up and down. But then we use a forward slash line instead of a simple fraction line in the middle there. And that / is the 456 prefix or the punctuation prefix, and then the 3/4 fraction line. Complex fractions, which we'll certainly come back to more at kind of the middle school level later, but they're a thing too, right? A fraction can have more going on than just a numerator and denominator. In the numerator, you might have a whole fraction, and in the denominator, you might have a whole fraction. So here I wrote the complex fraction 1/2 over 3/4. You see it's pretty long. It starts with the indicator that I'm opening my big fraction. I open my big fraction with a capital fraction opener, right? So it's a .6 in front of my 1,456. And then because I have a fraction in the numerator, I open a regular fraction in the numerator with another fraction opener, just a regular one without any prefixes. I write my 1/2 and close that fraction that is 1/2. Then I need the fraction line for my big fraction. To make the big fraction line in my big fraction, I write it as a capital fraction line. It's so intuitive, you just can't get better than this. .6 and 3/4 for the big line in the middle of my big fraction. Then I open my little fraction for the denominator, since I put 3/4 in the denominator, write 3/4 and close that little fraction. And when I'm all done, I have to close my big fraction too, matching that first prefix I opened up to close that. Now, if that all made your head spin a little bit, here's a more visual way to look at that. And you'll note that in this kind of handout, which you can download if you are taking class with me, if by some strange feature of the internet you have found this video and you're not actually in my class, you can screenshot this and enjoy it to your heart's content. In the fractions handout, the colors of the pieces of the fraction are mirrored in the Braille so that you can kind of help yourself hone in and look at each specific part and how they're related. And so you can see there in the complex fraction where maybe the big fraction line is blue. Also, the big opener way at the beginning is blue, and the big closer way at the end is blue. So you can follow through all the pieces that are needed to nest multiple fractions together. Once you get the feel for how it works, it's very easy and straightforward to transform any complexity of fraction into a nice linear string that works in Braille. But there's a more visual way to see it if hearing it makes your head swim. Let's talk a little with upper elementary about some important punctuation. It's important to keep remembering that a mathematical comma is .6. So when you see a .6 in a number or after a number, the numeric mode meaning for that is often mathematical comma. And the mathematical dot or decimal point is 4/6. In these grades, students often start learning to graph things. And so ordered pairs become really important, where you have kind of the X value and the Y value that you could find a place to plot. To do that, we group things inside of our Nemeth grouping indicators, which are based on the contraction shapes for of and with. That pair of shapes together make the open and close parentheses, and all of its fun curly or square or angle derivations by just adding the appropriate prefix to change their shape. When you use those grouping indicators to enclose a set like an ordered pair, or even a larger set like a set of numbers that are separated by commas, that enclosed list automatically sets numeric mode, and this is another place where you won't have to use numeric indicators throughout. For Cartesian graphing, it just sets the numeric mode for you. It's important if you are teaching students who are blind or visually impaired to teach both the Braille, right? How do we write an ordered pair? How do you tell which value is the X and which value is the Y? But also the graphing. Students who are sighted will see graphing on the board. They will see teachers model it and walk through the steps. Students who are blind might need a breakdown of those steps, right? That learning at a distance and observational learning can be impaired and can be a place where we need to provide instruction that they can access so that they can get the concepts. This could mean modeling it on Braille graph paper so that they can see all the graphing and follow along, doing it with push pins on Braille graph paper. doing pegboards with latex-free stretch bands like rubber bands, but not rubber in schools, obviously. Doing pegboards so that you can stretch from one point to another point to another point and make kind of the arc of the graph or the outline of a shape. I know kids often will have, when they are learning to graph things, worksheets that say plot all of these points and see what it makes, and it makes some geometric shape or some picture that they plot out. The same can be done using a pegboard and stretchy bands to plot out all the points and find out what the shape is for a Braille reader. You could put wiki sticks on Braille graph paper or another system, or use a drawing board where you press down on the top on that thin plastic sheet and it pops up the graphics so that the student can feel it in real time as you're drawing or as they're drawing and explore those relationships. To Braille ordered pairs, you'll open the parentheses, write the first number, no numeric indicator needed. It's clear that it's a number because it's inside that grouping indicator enclosed in a list, and because it's in the lower part of the cell, right? So it's really clear that it's a number. The comma, which is .6, and then the second part of the ordered pair, whatever the Y value is, and close the parentheses. If you had a whole list of ordered pairs, you would use the mathematical comma in between those ordered pairs. Again, note that the numeric indicator is not needed, and every time we use the comma in Braille, it is followed by a space. This is another way that Braille readers have good clarity that the .6 is a comma in this context and not a capital. So be sure to put a space after the comma inside the ordered pair and a space after the comma in the list between ordered pairs. All of our grouping signs in Nemeth are basically built on that of and with shape. You can put prefixes like a .4 or a .46 in front of them to change the shape of those grouping indicators. If you wanted angle braces or curly brackets or square brackets, you can do that with different prefixes. Adjacent to a grouping indicator, enclosed in a grouping indicator, Nemeth does not allow for use of alphabetic contractions. So spell those words out, or if the entire thing is enclosed in text, use the UEB group signs rather than the Nemeth group signs. Of, for, and, the, with, in, and be also had very special rules in the original Nemeth code to limit their use and make it clear and not get confused by them. That's changing a little bit with the new Nemeth being in UEB context, and one of the rules they put in place with the UEB switch indicators was that then you couldn't use contractions in Nemeth. So depending on the age of your textbook when it was transcribed, if you're using a geometry book with a student that the school district or the state has had for a while that's in the Nemeth code, you may either see those old Nemeth contraction rules being used in Nemeth passages without the switch indicators, or if it's been brailled more recently and the switch indicators are used to switch from UEB into Nemeth, you might see that contractions just aren't being used in Nemeth and that space is being wasted. If the phrase begins or ends with numbers, in traditional Nemeth, we've used the Nemeth group signs. When I give out assignments in class, I usually am doing it for students to learn Nemeth, so I'm usually structuring things in the graduate classes so that you'll need to use the Nemeth group signs in class because that's what you're practicing. You already know how to do UEB. You learned that a different semester. Remember that these group signs do work to trigger numeric mode. So a number unspaced from them does not need a numeric indicator. Depending on the structure of the equation, you may or may not need one later on if there have been spaces. Some examples of grouping signs. My first example shows 9 plus 5, and for clarity, it would never be read as in plus enough because of those rules limiting how contractions can be used inside a Nemeth passage. The same equation though, the 9 plus 5, if I were to braille that out in UEB technical, would be 10 cells in UEB technical as compared to the 5 that it is in Nemeth. So if you just take a minute to consider kind of basic quadratic factors, a normal part, which not a normal part of 3rd through 5th grade, but is the extension of this 4th and 5th grade skill when you get to pre-algebra and algebra, that those quadratic factors, the pairs of added things, being equal on both sides, even if it's just ax plus b times cx plus d equals ey plus f times gy plus h in their parentheses, so like a standard set of quadratic factors, that's 28 cells in Nemeth. No problem. You can write it, you can solve it, you can balance it, you can do things to both sides until you've solved for whichever side you want to solve for. If you try and write that out in UEB Technical, it is 48 cells. So while 28 cells in Nemeth will fit even on a narrow piece of Braille paper and certainly give you room to work and manipulate on a 40-cell wide page, that's 8 cells too many for even a wide Braille page in UEB Technical anyway. So anyway, just a little comparison to the benefits of the specific style of space saving that Nemeth opts for. Inside grouping indicators, if they're paired like that, the open and close, if you have a letter inside there, you do not need any English letter indicator or grade 1 indicator inside of it. But if there's a whole phrase, then you would need an English letter indicator for a letter, even if it was starting right after it. So kind of some limitations on boundaries on the assumed numeric mode that it starts. Enclosed lists can skip those indicators, whether the list contains simple letters, numbers, equations excluding signs of comparison, right? So if it says 4 plus 3, that's fine. If it says 4 plus 3 equals x, not so much, and commas. So if it's a simple enclosed list, then you can skip grade 1 indicators and numeric indicators throughout. Powers and subscripts, or superscripts. Superscripts are the ones written above the line. Subscripts are the ones written below the line. We usually don't get to subscripts below the line in 3rd through 5th grade, but getting to powers starts now. So this is where students square things, cube things, take things to the power of 6, or multiply by 10 to the power of 8, whatever that number may be for their class. Powers and superscripts are a mode change in Nemeth. And the mode change, so you're writing along on your baseline and you go to a mode change that says now you're writing in a superscript, you're writing up above. And that continues until it's terminated. If you've already studied UEB Technical, this is exactly the opposite. UEB Technical says this only applies to the next one thing. In Nemeth, it's salient. It sticks there until you turn it off. So you've turned on go up a level, and there you stay until you say come back down. You can terminate that with a multi-purpose indicator. And in this context, Braille readers often will kind of call it a baseline indicator because it sends us back to baseline. Reminds me of the octave indicators in music. So you may hear that terminology from students or from blind adults who are Nemeth users. The formal term is multi-purpose indicator because .5 means different things in different places in Nemeth. But in this place, what it's doing is bringing you back down to the baseline. Powers and superscripts can also be terminated by a space. We do not generally assume that a power continues through a space. So when there's a space in Braille, the power is done, the superscript is done. If you're at the end of an equation, the end of a line, that also ends it. You don't need to terminate at the end of lines. We're all about saving space. To raise up to a power, you use dots 4, 5, and that tells you that the next thing written is written up high. And again, it'll stick around for a while. We'll build on this more in future units. Here are some examples of powers, though, and really what that coming back to baseline is about. So if my first example here is the number 2 to the power of 4. My second example is 3 to the power of 2. So you have a sense for how that looks and how kind of the space looks bigger when you have a number that's just on the left side of a cell versus when you have a full width letter. But that is a dots 4, 5, so it's over on the right-hand side of the cell. And then an equation, like a practical application. So I have 9 squared plus 1 equals 82. Perfectly logical. I have 9 to the power of 2, And then I have that .5 because there's not a space after my 9 squared. There's a plus sign after it. And I need to know to come back down to baseline and read that plus sign. Plus 1, and space equals space because we always have spaces around our signs of operation. And the answer is 82 because 9 squared is 81. I added 1 to that, I get 82. Now what happens if I don't put my baseline indicator in? Doesn't work the same. So if I have 9 to the power of 2 plus 1, and I don't put a baseline indicator in there to come back down to baseline before the space, what happens is, look at that print equation, it's 9 to the power of 2 plus 1. That's the same as 9 to the power of 3. Now my whole plus 1 is up in the power, and that changes the meaning. Now instead of adding 1 to the 9 squared, I'm adding 1 to the 2 and taking 9 to the power of 2 plus 1. Well, that's 729. That is a very different answer and very different equation than if I put that little .5 in there to bring my plus sign back down to baseline. That's the size difference it makes whether or not you have a .5 after a power or a .5 in your equation to come back down to baseline. It is a sneaky little dot in the sense that there is no print equivalent for that. It just changes where you write the plus sign next, whether you write it up high or down low. This is, by the way, exactly how superscripts work in something like Microsoft Word. So I am so impressed that Dr. Abraham Nemeth had this all figured out in the era before computers. And he clearly was a budding computer scientist, thinking computers before computers were ubiquitous, because we often see kind of this parallel in how Nemeth works and how computers actually treat things in a very linear way. So same effect, make sure you come back down to baseline if the print equation has the numbers on baseline so that you don't end up with half of your equation up in the power and drastically changing the meaning. Even when it's only 1 that you're adding, you see that's a huge impact on the result. 3rd through 5th grade is also the heyday of Abacus for blind students. Abacus is a wonderful little tool that I think really helps with early numeracy for any child who learns it, but has stuck around in the blind community for some good reasons. So if you are advocating with a school district, with teachers, with families, that an upper elementary child should be learning and using Abacus throughout their math classes, you might get some funny looks if other people haven't seen it. It's just a tool with movable beads that you can use to do scratch work. It's not quite the same as using manipulatives. It's a little more base 10 than that. There are 5s and pairings with 5s that end up mattering a whole lot so that your number sense gets really, really developed when you work with math this way. But why do blind kids use them? This is not The Cranmer abacus is not an abacus that will solve any math problem for anyone ever. You can't multiply on it or divide on it without knowing your multiplication facts or division facts. It's not like a calculator where you punch in the numbers, it does some math and helps you along. The Cranmer abacus for students who are blind is like scratch paper. It is the paper and pencil where you write down the intermediary steps of your problem between deciding what problem you're going to set up and having the solution. You still have to do all the steps, but to do all of the steps and write them on a Perkins Braille writer for things like multiplication or long division, the amount of scrolling up and down to write on multiple lines when you carry one and cross something out and borrow and subtract, that up and down lines is very tedious on the Braille writer. It's not tedious on an abacus. So you still have to do all of the steps, and you might need to advocate to teachers that the child is still doing every single arithmetic step to get to an answer, but they're doing it in a way that is efficient and tactile, and at the end they can write down their answer on their Perkins Braille writer or write it down in their Word document, but the Abacus lets you solve the equation step by step without taking up copious amounts of paper and a whole lot of time, frustration, and confusion along the way. I sometimes point out to teachers that in modern math curriculum, we accept a lot of different ways to get to a right answer. If a student is adding long numbers, they can do it in the ones column and then the tens and then the hundreds, or they can do it in the hundreds and the tens and the ones and then regroup at the end. They accept both of those ways. Abacus is just another kind of methodology for writing it down, but it's only the scratch paper and the pencil. It is fantastic. If you are a parent, teach your kids to use Abacus from the time that they are little until they're too old to calculate any arithmetic by hand, and they will have much better number sense than kids who have only ever done it on paper, because the base 10, base 5 combination is really, really good for developing number sense in any kid, but especially in blind kids in that upper elementary age. They should be using their Abacus, and they should be allowed to use their Abacus as their scratch paper to do their work. This should be a replacement to any requirement to show their work on repetitive problems. By all means, if a kid is getting the wrong answer, have them show their work once so that you can analyze it and see what step they're getting wrong. But for the there are 20 math problems to do kind of worksheet, an Abacus should be allowed, permitted, replacing all of that writing down the steps to solve the work for students who are Braille readers, because it is much more efficient, and unlike handing them a talking calculator, does not supplant any of the arithmetic work from them. It just makes the work accessible, and that's the goal. Until next week, happy Brailing!